Physics reaction video number 72. This time I literally did a search for this phrase, motional EMF, and found something. So let's see, am I out of the way? Yep. All right, so here we go.
Now the motion of a conductor through a fixed magnetic also causes induction. This kind of induction is called motional EMF.
Excellent.
So we're going to consider this circuit in this image here. We've got two conducting rods on top. They're connected on this end by a resistor, and on this end there's a metal bar running across. So all of these pieces.
Quick pause to talk about technology here. So picture in picture, which is awesome. Her mouse is a little hard to see, sort of if you compare it to the size of my mouse, right? It's sort of, I wonder if she just has a bigger monitor or something. But you know, all of this is super easy to read. And I tell you, this is one of my favorite problems, so I'm super excited to see this.
Pieces create a closed circuit. And this circuit lives inside a magnetic field shown here. Okay, so as this vertical rod here moves to the right, the area that is enclosed by this circuit increases. So our magnetic flux is...
And I just noticed, if you watch her, she goes from looking at her screen, which is I think over here a little bit, to looking at us. So, you know, her picture's a little small, about the same size. I guess mine's even bigger, right? Where's mine? About, well, off to the right there. But I think that this, you know, there's a huge cost of putting your picture in here, right? So these videos I've been making are gigantic in file size compared to the ones I make where I don't turn my camera on. So there is a cost, and yet I think it's probably going to be helpful to go up there and look at her. My guess is she might use her hands or arms at some point, and of course facial expressions, all of that stuff. So it's a really interesting thing to think about. I'm curious what you guys think about that. You know, what would you think, for example, of these reaction videos if there wasn't me, a picture of me there for you to look at me. So the other thing I want to talk about is this convention that we use, right? These little circles with the X, meaning this is a magnetic field going into the page. I always tell my students, think about an arrow. If it was flying away from you, you'd see the fletching in an X pattern. If it was heading towards you, I guess you'd just see the tip. It's not great. You see the fletching either way, but I know that some students start thinking that the magnetic field is always into the page, because frankly we almost always use little X's. So we'll keep an eye out to see if she has any examples where the magnetic field is going in a different direction.
Equal to the magnetic field times area. So if the magnetic field stays the same but the area increases, we increase our magnetic flux. So if we look at Faraday's law, ignore the sign on it for now, and consider one loop, then the EMF we induce is equal to the changing magnetic flux over time. We said magnetic field was stationary or constant. The area is changing, so that's a changing area over a changing time. Okay. Now the area we can write as the length of this rod times some distance that it's moving through horizontally. Okay. So
just going to pause here. My guess is she's going to do an example of it, if not in this video, a future video. But I'm always struck by the fact that in this frame, in this frame of reference, if you've got this bar going this way, you literally can look microscopically and say, hey, electrons, what are you feeling, right? And you can use the left-hand rule. I'm going this way, V's down. So that's going to drive the electrons down, and if they're driven down, they're not going to pile up, they'll just keep on squeezing around, right? So this EMF, this notion of driving a current, remember the current goes the opposite direction of the electrons, damn you, Ben Franklin. For this example, we talk about how we've created this really interesting EMF, and some people talk about the you know, think of this as have units of volts, right? There's this crazy voltage around here that's super hard to measure, but really microscopically it's really easy to explain to students, right? The problem comes when you stop treating this as a constant and just everything's sitting still and you just turn up or turn down the magnetic field, because then you have to ask microscopically, hey, electrons, what are you feeling now? And they're like, well, I'm not moving, so I don't stinking care about that magnetic field. Yeah, but it's changing. Whatever, I'm not moving. And all of a sudden you're like, whoa, the light bulb lit, right? So to me, motional EMF Motional EMF is easier than changing magnetic field EMF. So I'm curious what you guys think about it, even though the mathematics is the same. And I think it's Jackson, the famous graduate book for electricity and magnetism, talks about how the other one, when B changes, has units of electric field. The electric field, it's basically the electric field that is in this direction here. Has units of the electric field, kind of acts like the electric field, but it almost seems like it's its own thing. So I find that really, really fascinating.
We're going to write that as BL delta X over delta T, because L is stationary, X is changing.
Cool.
The horizontal distance there is changing. And remember that a change in position over a change in time, that's a velocity or speed.
Like this, by the way.
So we can write this motional EMF as the magnetic field times the length of some conductor times the speed at which that conductor moves. Now this is a special case where the magnetic field and the magnetic field and this length of my bar here and the speed are all perpendicular to each other.
Which you can do because we live in 3D.
Lenz's law will give us the direction of the induced magnetic field and current. And our right-hand rules, we're going to use both of them, give us the direction of the current and the magnetic force on the bar, which we're going to practice with the problem here. So we have a sliding bar, this bar here, with a length of 0.5 meters, and it moves at 2 meters per second in a magnetic field.
All right, half a meter. Okay, doesn't quite fit in my in my little image here. Half a meter, moving at 2 meters per second. 1001. So moving 2 meters per second. So, okay. All right, what is that? I don't know. Not that fast, 5 miles an hour or something. Magnetic field of 0.25 Tesla. That's a pretty powerful magnetic field. Okay. So I would expect, because it's a really long bar, moving pretty fast, at least compared to like my hands here, really strong magnetic field. I expect, find the induced EMF. Only a 1/4 volt. I'm surprised. I guess I would have expected more. 1/4 volt. Oh man. So if you had to replace your battery died, and you were trying to do it with a setup like this, you'd have to multiply. I don't know. I guess I don't know what the voltage of a cell phone battery is. Let's say it's a couple AA batteries. I'm embarrassed. I don't know, but I know this is how much you charge it with. So your charger, I think, is 5 volt charger. This is embarrassing. I don't know. Let's say we have to get 5 volts. We'd have to do 20 times. With one of these, would have to be 20 times bigger. This 20 times bigger is not an option. This 20 times bigger, that's tough. This 20 times bigger is really hard. That's fascinating. Okay, let's keep going.
Field. Here, this magnetic field is into the board of a magnitude of 0.25 Tesla. We're going to find the, induced EMF and current in the moving rod. Calculate the magnitude and direction of the magnetic force on this bar.
I'll just pause and talk about that, right? So my guess is she typed this up. She meant to say induced. She wrote inducted. And as soon as she saw it, I wonder if we can go back and see her eyes. It's probably too hard to see, but there was a moment where she's like, right? And then all she did was say, let's just say induced, right? So it was super smooth. Loved it. I thought that was really, really great. As I always say, we can't expect no mistakes. We just have to wonder how to deal with them. And I thought that was really smooth.
And then calculate the magnitude and direction of the force we have to apply to move that bar at constant speed of 2 meters per second. In this problem, we're going to use the motional EMF to find an induced EMF and an induced current.
Is she going to write on that? Oh, yeah, look, it's a frame. Okay, so my guess is she's right-handed. On average, most people are. So if she starts writing with her left hand, that's that super cool thing where you flip the video. I'm excited about this.
So we have a conductor here, a conductor here. These are connected by a wire over here with a resistor. And then these two parallel conductors are also connected by this conductor here.
By the way, I think this problem is really, really interesting because you have to put this resistor over there, frankly, just so that people don't freak out, right? Like, oh, wait a minute, you say there's a current flowing and it's going to heat the world and die. No, don't worry. We put a little light bulb over here. We're good to go. Even though we pay very little attention to it, unless we really try to figure out, like, power dissipated, right? So we'll see if she gets to power dissipated. But yeah, I'm pretty sure she's right-handed. I'm pretty sure this is a mirror image of her. Oh, this is so cool.
This is a bar that I can slide in either direction.
And she's looking
And
at
when
us.
I move this bar, that's going to induce a change in magnetic flux within the loop. And that's going to induce an EMF, and that's going to induce a current. So this sliding bar has a length of 0.5 meters, and it moves at 2 meters per second.
Okay, I'm just trying to find some identifying marks in case she goes, maybe we'll rewind. Let's see, we're at 401. So the part in her hair is on the right side as we're looking at it here. So if we go back, 401, I can come back to 401. Oh, I can't quite see where the part in her hair is here. Is there anything else we can see that tells us? Looks like there's more hair over here. There's a little bit more hair over here than over here. So I think this 401 is I think this is a mirror image. God, that's so cool.
Meters per second to the right. So somebody is grabbing it and is moving it to the right.
I've always thought about doing this. I've just never had
And we've got a magnetic field inside the loop here, a magnetic field that has a strength of 0.25 Tesla, and the total resistance of my circuit.
Sorry, I'm just so fascinated. The first time I saw anybody do this, I thought, how in the world are they so good at writing backwards? I mean, that was my first thought until I noticed that everyone I ever saw doing this was left-handed, I think. And that's when I was like, oh, so we talk about post-production all the time, right? Somebody has to do some post-production here. Although if you're using OBS, probably OBS will automatically flip it for you. I've been actually looking to that to make my image be flipped. Couldn't find it, but I'm sure it exists. So you could do some on the, in the moment flipping. Very cool.
Is 0.5 ohms. So our first part of this problem is to find the induced voltage or the induced EMF in the moving rod, question mark. To solve this problem, we could go right to our equation for motional EMF, or I can show you how you can get that equation for motional EMF from Faraday's law of induction.
Oh,
so,
cool.
If we think about just think about the magnitude of the induced EMF. So we're not going to put the minus sign here in this equation on it. It's going to be equal to N, which is the number of turns of our loop. There's only one here, times the change in magnetic flux over the change in time. Okay. Now in this problem, the magnetic field here is not changing, but the area is. As I slide this conductor here back and forth, I'm changing the area enclosed by the loop. So our change in flux is equal to delta B A cosine theta. So anything in here could change the flux. B could change, A could change, or this angle theta can change, which is the angle between my magnetic
She's got
field
dots over them now. It makes
and
me think time
perpendicular
derivative.
to the loop. So in this case, perpendicular to the loop and my magnetic field are aligned with each other.
Here's the thing that the mirror doesn't help with. Did you notice that? So she seemed to be indicating that the magnetic field was coming out towards us. Because as she's looking at this, she's looking at X's, which means magnetic field going away from her. Whoa. Let me think about this. Because to us, the magnetic field is definitely going into the page. Could it possibly be that she's going to get the wrong direction of the current? Because in her mirror world, the way we're looking at it, I actually think so. I think right hands become left hands. So when she says she's going to do the right hand rule, she's going to use her left hand Whoa. No, she's going to use her right hand because she's going to think right hand. To us, it's going to look like a left hand. And she's going to get the wrong answer. I'm going to keep going, but I keep thinking about that.
So theta is 0, cosine of 0 is 1. Okay, and then we've got delta t here. So in this problem, b is a constant. It is not changing, but a is changing. So we can pop b out of our delta symbol. So b times the change in area over the change in time will equal our induced EMF.
So there's
but let's
definitely
imagine that I'm moving this rod. As I move it, I'm going to move at some increment delta x. So remember, maybe from last semester, that v is equal to delta x over delta t.
Maybe from last semester.
The speed at which I'm moving my bar here. So b delta a over delta t. So b times, okay, the change in the area enclosed by my loop is going to be the length of it times its width. So the length here is not changing. That's L. And then, but I do have, actually, I can remove this delta here because L is not changing.
Oh, it's trying to erase it, looks like.
We are changing the length here of the bottom part of my loop.
So getting back to that other way of saying it, like microscopically asking these electrons, hey, what are you feeling? It's really weird, right? Because these microscopic electrons have no idea how far away this thing is, right? So to anthropomorphically say, hey, electron, what are you feeling right now? The math that we set up for our students says, well, you got to figure out this area. It totally depends on this area. It doesn't actually depend on the area. It actually just depends on how it's changing, right? So it's really, really interesting to think about anthropomorphizing things, but that's not, I mean, if you don't like that, just think about it like microscopically. What force is this electron being exposed to? Why should that matter how far away this resistor is, right? So it's really, really subtle. But I think that she's doing a really great job of very carefully figuring out how to apply this delta to the area, because she's like, oh yeah, L is constant. She's trying hard to get right to this, right? And I think that she's doing a great job of it.
So we can replace that as delta x. So this is our length times width, okay? And then we're dividing it by the change in time.
Cool.
All right. So my area, at least the width of my area, is changing. That's the increment that is changing along the width, okay? So delta x. So we've got b L delta x over delta t. So remember that delta x over delta t is v.
Derivatives are just fractions.
My motional EMF, the magnitude of it, is equal to b L v.
Super easy.
The magnetic field, that's not changing, times the length of my conductor moving through the field times the speed at which I'm moving that conductor inside the field.
Okay, so let's figure this directionality stuff out. For us, the way we are seeing it, I'll just do my right hand. Oh, I'm flipped too. So the V is this way, B is in, so right-hand rule is going to say that the current is going to flow up. So I believe this is going to cause a counterclockwise current in here. She sees it, oh man, I just can't do it in my head. Oh, I've got a mirror. She sees it like this, right? So she sees it like that, and she's going to say, okay, and I'm going to use my right-hand rule looking at my mirror, be going that way. She's going to call it counterclockwise, meaning moving away from the bar this way. That's going to be wrong. Whoa, I never thought that we'd have problems with this mirror setup. I'm super curious to see how she deals with that.
That's my motional EMF. So that's going to equal,
I'm just going to skip to it.
my magnetic, which was 0 second here. So there we go. Now we can go ahead and think about the induced current. my induced over R 0.255 ohms.
I want to get to the direction. I don't know if she
amperes.
actually is going to do the direction.
Which direction
Here we go.
is my current going to be within this circuit? Because my change in flux is increasing, B is staying the same, but my area is getting bigger as I'm moving my rod to the right here.
Okay.
Delta phi, my change in flux, is increasing. So let's remind us that delta phi is increasing in this problem.
Love it.
So a magnetic field will be induced due to a current in this loop here that will want to oppose this change in flux.
Okay. So to us, it's increasing into the screen. To her, it's increasing towards us, right? Towards her camera. And so we want the magnetic field due to this loop to fight against that change. So we want some current that comes out of the page. So for us, that's going to be counterclockwise. Okay, so counterclockwise is the answer. So think up in this bar. Up in this bar.
Flux. So if the flux is going up, my magnetic field is into the board. Okay. Nature abhors a change in flux. It doesn't want this flux to change. So it's going to want to try to counteract this increase in flux by inducing a magnetic field that's going to be pointing in the opposite direction inside the loop as the magnetic field. So the permanent magnetic field is into the board here. So my induced magnetic field is going to be pointing out
Okay.
of the board.
Okay.
inside
Yep.
the
So far,
loop.
so good.
So my induced magnetic field, this is my induced magnetic field inside the loop here, is going to be pointing out of the board toward me. Okay? So if it's pointing out of the board toward me, my induced magnetic field, I got my fingers here, second right hand rule, my fingers are going to curl around the direction of the magnetic field. It's going to go out of the board toward me above the loop. So that means that my thumb is going to be pointing off in this direction.
Wait.
So
She was using what she thinks of as her right hand. What was she just doing there? Oh my God, this is so cool. Okay, so the way I would do this, for the way this is, I would say, okay, to be able to achieve a magnetic field towards us right here, to be able to achieve a magnetic field towards us, I need a current flowing this way. She said, I need a magnetic field flowing towards her. She used her left hand. Man, I'm confused.
the induced current is going to be pointing in this direction.
Yes.
This
That's
is,
right.
A counterclockwise current.
Whoa, okay, so she just called it a counterclockwise current. There is no way it looks like a counterclockwise current to her. That does not look like a counterclockwise current to her. That looks clockwise. Okay, I gotta stop. Gone too long. Help me, you guys, help me. I don't think I'm doing this right. I really, really thought that her approach, if she used her right hand, which to us looks like a left hand. Oh, my mirror thing was wrong. It doesn't look like a mirror to her. It looks correct to her. We're... Okay, my head hurts. All right, you guys. This is so cool. I really, really loved how careful she was with this delta A. I loved the setup. I loved how she, why not? Let's just do everything mutually perpendicular. So many cool things about the way that she presented this. And I'm just the one who's super confused here at the end. All right, everybody. Have a great day. And remember, physics teachers are awesome.